we can, okay. So hello everyone. So my name is Weixin Zhang, and I work for the Microsoft AI frameworks. And today my topic is around ONNX and ONNX Runtime. So here is my agenda. First, I will talk about what is ONNX, and then how do we use ONNX in Microsoft. And the third is what is ONNX Runtime. The last one is how will you create the ONNX models. So it is relatively straightforward if we have just one or specific training frameworks or one specific hardware platform. But if you come with a variety of frameworks or a variety of hardwares, so it will be very hard for you to support these combinations with high performance. So that's the reason ONNX came out. ONNX was initiated by the Microsoft, Facebook, and Amazon. So ONNX is short for Open Neural Network Exchange. It is an open format for the machine learning models. For now, ONNX has around 30 partners. So you can see some cloud player or some hardware vendors. ONNX was designed based on the 4 key design principles. First, it not only supports the deep neural networks, but also supports the traditional machine learning. Second, it is flexible enough to keep up with the rapid advance. Third is it is compact and cross-platform representation for serialization. The fourth is it's standardized for all of well-defined operators, which is used by the real user model. So ONNX spec, as I said, we honestly support both deep neural network and traditional machine learning models. So it composes 2 parts. One is the file format, another is operators. For file format, it is composed of 3 parts. It's a model, graph, and a computation node. So on the right side, you can see this is a viewer of the one machine learning model. For model, it has version information, metadata, and it also is acyclic graph computation. For the graph, it has inputs and outputs. It has a list of computation node, and it is also graph name. For the computation node, it has 0 or more inputs of the input, and it must have 1 or more output. It is an operator, and the operator has some parameters. For the data type, we support 2 kinds of tensor type. One is tensor, the other is non-tensor. Non-tensor is for the traditional machine learning model, for example, sequence and map. For the tensor type, from the element type point of view, we support an integer, sign, unsigned, float, or double, etc. Operator is undefined by the name, domain, and version. For ops, we have 2 kinds of ops. One is called the core ops, the other is called custom ops. For the core ops, it should be supported by the ONNX compatible product. It is generally cannot be meaningfully further decomposed. Currently, we support 124 ops in the AI ONNX domain, and the other 18 in AI ONNX.ML domain. ONNX supports many scenarios, including image classification, recommendation, and language processing. On the right side, here is a simple example for the op called ReLU. Yeah, ONNX also supports functions. Functions is a combined ops built with existing primitive ops. So runtime framework or tools can either have optimized implementation or fall back to using primitive ops to support function ops. On the right side, you can see this is a simple example. This function opt can be fallback to MATLAB plus add. Or the tool or framework can support this function natively. Okay, next is how do we use ONNX in the Microsoft? In the Microsoft, we have a lot of teams and a lot of external customers. And we have a lot of models training from lots of different frameworks. For example, TensorFlow, PyTorch, etc. And we also need to target the different hardwares, for CPU, GPU, FPGA, and etc. So for ONNX in the Microsoft, we have 3 platforms to use ONNX. One is Azure ML, VML, and ML.NET. And we also have a bunch of products using ONNX, for example, Bing, or Cognitive Service, or Office, and etc. And during the past 2 years, and based on ONNX, we developed ONNX Runtime. And with using ONNX Runtime, we saw the performance gain up to the 14.6. And we have 100 million devices running ONNX Runtime. And also we have billion requests that is handled by the ONNX Runtime in Microsoft Surface. Here is, I'm going to give 2 examples. One is Bing Q&A. In this service, we are using 2 models. One is BERT-based. The other is a transformer with attention-based. To use ONNX Runtime, we saw around 2.8x perf gain. Second one is for the Bing multimedia. So this model is called the image embedding model. So with ONNX and ONNX Runtime, we saw 1.8x performance gain. Okay, now is based on ONNX, and we have ONNX Runtime. ONNX Runtime is an implementation for the ONNX. ONNX Runtime is high performance, cross-platform, and lightweight and modular. And it also extensible. Yeah, first, ONNX Runtime is high performance. Second is extensible architecture to plug in optimizer and hardware accelerators. It supports 4 ONNX-ML spec from the version 1.2 up to 1.5, and ONNX 1.6 will be released in this week. And it works on Mac, Windows, and Linux. And from the hardware point of view, it supports CPU, GPU, and currently we support Intel Edge device and NVIDIA Jensen Nano. And also we can run on the ARM CPU. And for the API point of view, we support Python, C#, and C and C++. ONNX Runtime is written in the C++. And the last 2 is we support the code generation in ONNX Runtime, and we are working on support training in ONNX Runtime. Here is a brief view of the architecture of ONNX Runtime. ONNX Runtime is composed of 3 key components: graph optimization, graph partitioning, and execution provider. So during the initialization stage, so ONNX model will be loaded to ONNX Runtime, and then we will have an in-memory representation for the model. And based on this IR representation, we will apply the graph optimization. In this stage, the optimization is the exemplifier independent. And after that, we will send the whole graph to the exemplifier to do the graph partitioning. And after that, we will apply the exemplifier specific optimization. And then we will pass this information to the executor. We have the parallel executor and the sequential executor. At the bottom, you can see now we support a bunch of execution provider. For example, CPU and GPU. GPU is CUDA, now it's NVIDIA. And also we support TensorRT and ngraph. ngraph is from Intel. And also I didn't list the other two, and you will see later. And also we support the Intel OpenVINO now. Yeah. So here is the IR in the ONNX runtime. So basically there are three structures. One is a model, and the second is graph. The last is load. It is a in-memory object mapping to ONNX model file format. It offering APIs to read or write computation graph. Besides, we have a structure called graph viewer. It is a read-only view of the computation graph. It is used in two parts. One is in the execution provide API. This API is between the runtime and the hardware accelerator. The second part is a module evaluation. It is applied after model optimization and partitioning. Okay, now it's graph optimization. We support two interfaces for graph optimization. One is called the rewrite rule. The second is called the graph transformer. Rewrite rule is created for finding patterns and applying rewrite rule against a subgraph. For graph transformer, it is an interface created for applying graph transformation with full graph editing capability. Just like the compiler, we support 3 different levels for the transformer level. Level 0 is for characteristics. For example, when in the heterogeneous environment, we may partition graph into make it run on the CPU and our other device. So between the device, we need to do the data transformer to do the data transfer. So for the transfer, we probably need to insert the memory copy. For level 1, it is the XM provider independent. So level 2 is XM provider specific optimization. Okay, for graph partitioning, given a mutable graph partitioner assigns a graph node to each XM provider per their capability. And the ideal goal is to reach the best performance in the heterogeneous environment. ONNX runtime uses a greedy node assignment mechanism now. It uses specific preferred XM provider list in order. ONNX runtime will go through the list in order to check each provider's capability and assign nodes to it if it can run on that node. In the future, we plan to improve this part by using profiling-based partitioning or machine learning-based partitioning. Okay, now for the execution provider, it is a hardware accelerator interface to query its capability and get corresponding executables. For now, we defined 2 categories. One is called the kernel-based execution providers. For example, CPU execution provider, CUDA EP, or MKRD EP. These EPs provide implementation of operator defining the ONNX spec. Second is runtime-based EP. These EPs this EP may not have implementation with the granularity of the ONNX spec operators, but it can run with the whole or partial ONNX graph. For example, it can run several ONNX ops together with one function it has. For the execution provider, we have an structure called the node computation info. It is this structure carries executable written by the runtime-based execution provider. As I said, we support several API, Python, C#, and also C and C++. Here's the example for the ONNX Runtime. So the API is very simple. First, you just need to inference session to initialize the model, and then to just run for the inference. So for the code generation, ONNX Runtime added the code generation inside. So at present, the code generation is TVM highlight based. It is used by two EPs. One is NeoFire EP, the other is CUDA FPGA EP. NeoFire EP is already open sourced. It is developed for the CPU target and with quantized inside. For the, if you guys interest, you can to look at the details in the repo, ONNX Runtime repo. And basically, what are we doing is for the code generation, we'll lower ONNX graph to the TVM IR, and then apply TVM schedules, or even we write our own schedules, and then do some optimization, and then generate the code, and trigger the kernel compiler, and then return the executable to the ONNX Runtime. So for training, the purpose to do the training is, first, it enables training on device. It helps reinforcement learning and quantized retraining. I think the people probably know, when you do the quantized model, probably you will lose the accuracy. So sometimes you need to do the retrain again. With the training, ONNX is a fast, lightweight runtime with both training and inference. For the inference standalone, the binary size is around 3 megabytes. Plus training is around 5 megabytes. Also, ONNX Runtime training also enables large-scale training for multiple front-end and back-end. So our target is to have a unified software stack to support front-end, for example, TensorFlow or PyTorch. For back-end, can be GPU or other accelerators. It will be a combined software and hardware stack. ONNX was initially designed for the inference. So originally, the ONNX or ONNX Runtime receives the inference graph, just a forward graph. Now, what are we doing is we add, after ONNX Runtime still receives the forward graph. After that, we will add a loss function. And then we build the gradient graph based on the forward graph and plus attach to the optimizer. After that, we'll get the whole training graph. And then it will run same as inference, just a graph. Okay, so next is, so how do we get the ONNX model? So typically there are 4 ways. First is you can get a model from the ONNX Model Zoo. Second is you can use service like Azure customvision. Third is you can convert existing models. Fourth is you can train models in systems like Azure Machine Learning service or other machine learning service. Here I just give a brief idea. So what is the model zoo looks like? Here is just several models listed in this page. If you can find more models from model zoo. Yeah, here is a few steps about how to use the custom vision service. For converting models, we have developed several tools to help an user to convert model from different toolkit. For example, from TensorFlow, Keras, or CodeML, or other framework format. Also, for the PyTorch and CNTK, we natively support this framework to export models to the ONNX format. Here's a few examples about using converting tools. For example, for Keras, or TensorFlow, or PyTorch, and Chandler. Last, ONNX and ONNX Runtime is open source, is a community project. So we would like to invite everyone to join, to get involved. For ONNX discussion, here's a link called Git. You can participate in discussion for advanced, for example, ONNX spec. For the code contribution, or we open source in the GitHub, both ONNX and ONNX Runtime. Yeah, that's my whole talk. So.
Yes, I have one question about the Jetson Nano support. So can you share a little bit more details about this part, because it is more related to maybe ARM or potentially ARM devices, right?
Yeah. Okay. Yeah. A good point. So for now, and as in my slide, I said we support that for example, Intel Edge device and Jetson Nano, and this is accelerator, and but from the platform point of view, the system could be run with the ARM CPU. So in the future, as I said, alternate support run ARM as well. So our point is to extend this alternate to from the cloud to desktop and to the IoT. For the, as I said, for the Jetson Nano, currently we have a excellent EP called the TensorRT EP. So we leverage TensorRT EP to support the Jetson Nano.
Are you using Linux on this? Which operating system is running on this kind of Jetson Nano?
For Jetson Nano,
maybe Ubuntu or?
Typically we run on Ubuntu.
Okay,
yeah.
Great. So it means that ONNX Runtime should have good support on Linux already, right?
Yeah.
Okay, great.
Yeah, we support Windows, Mac, and Linux.
Yeah.
Yeah.
Great. Thank you.
Yeah.
Can you talk more about the graph partitioner in the runtime that you were talking about? Like, how does it decide what area of the graph goes to which accelerator, and what does the runtime do?
Okay, so first of all, we will have a list of the EPs. So EP will be in the order. Second, we will pass the whole graph to these EPs. So each EP will have a function called the get capability. So each EP will return a connected subgraph that they can run. And then on runtime will decide the priority based on the order of the EPs, and then assign the corresponding nodes to the EPs. Yeah, thank you. Okay, thank you.